What is information? It sounds like a simple question, but it's not. We use the word all the time. We get information from the news. We store information on our computers. We give information to a friend when we tell them a story. In all these cases, information seems to be about meaning. It's about something. But there's another way to think about information, a deeper way, a way that has nothing to do with meaning. This way of thinking started with a man named Claude Shannon. He worked at Bell Labs in the 1940s. He wanted to solve a practical problem. How do you send a message over a wire without it getting corrupted by noise? To solve this, he had to ask a very basic question. What is the message, really? What are we sending? He realized that a message, any message, is just a selection from a set of possibilities. If I'm going to send you a single letter, I'm choosing 1 out of 26. If I'm going to flip a coin and tell you the result, I'm choosing 1 out of 2. Heads or tails. And Shannon had a breakthrough. He said that information is the reduction of uncertainty. Before the coin flip, you are uncertain. There are 2 possibilities. After I tell you heads, your uncertainty is gone. You have received 1 bit of information. That word bit is his invention. It's short for binary digit. A 1 or a 0. Yes or no. On or off. Heads or tails. This is the simplest possible choice. It resolves the simplest uncertainty, and Shannon showed that you can measure any information in bits. A choice between 4 possibilities like A, B, C, or D is 2 bits of information. A choice between 8 is 3 bits, and so on. Notice what's missing here. Meaning. Shannon's theory doesn't care if the message is a beautiful poem or just random gibberish. If both are the same length, they contain the same amount of information. A string of 1,000 random letters has the same information content as a 1,000-letter message with a profound secret. This seems strange to us. We care about the secret, not the gibberish. But for the engineer trying to send the message perfectly, it makes no difference. The task is the same. Send the sequence of choices correctly. So, on one level, information is just that. A measure of unpredictability, a resolution of uncertainty, a quantity we can measure in bits. This idea powered the entire digital revolution. Everything you are doing right now, reading these words on a screen, is happening because of Shannon's idea. These words are stored and transmitted as a long, long string of ones and zeros, bits. This is the technical definition of information, but it feels a little cold, a little empty. It doesn't seem to connect to the rich, messy world we live in. Or does it? Let's move from communication wires to the world of physics. Think about a gas in a box. The atoms are all flying around randomly. Now, think about entropy. That's a word people used to mean disorder or chaos. A messy room has high entropy. A tidy room has low entropy. Physicists have a more precise definition. Entropy is a measure of the number of ways you can arrange the microscopic parts of a system without changing its macroscopic appearance. In a hot gas, the atoms can be in a huge number of different positions and have a huge number of different speeds, and the gas would still just look like a hot gas to us. It has high entropy. A crystal of ice, on the other hand, is very ordered. The water molecules are locked in a specific structure. There are far fewer ways to arrange them. It has low entropy. Here is where it gets interesting. The math used to describe entropy in physics looks almost identical to the math Shannon used to describe information. It turns out they are 2 sides of the same coin. High entropy means high uncertainty. If I tell you a gas is hot, you still know very little about where any specific atom is or how fast it's going. There's a vast amount of hidden information in the system. Low entropy means low uncertainty. If I tell you I have an ice crystal, you know a lot about where the molecules are. They're locked in place. There is less hidden information, so information is like the opposite of entropy. Gaining information about a system is like reducing its entropy. If you could know the exact position and velocity of every single atom in a gas, its entropy for you would be 0. You would have perfect information. This connection was famously explored in a thought experiment called Maxwell's demon. Imagine a box of gas with a partition in the middle. A tiny, intelligent being, the demon, controls a tiny door in the partition. When a fast-moving hot atom approaches from the left, the demon opens the door to let it through to the right side. When a slow-moving cold atom approaches from the right, it lets it through to the left. Over time, the demon sorts the atoms. The right side gets hot, and the left side gets cold. This process would violate the second law of thermodynamics, which states that the total entropy of a closed system can never decrease. The demon seems to be creating order out of chaos for free, but physicists realize there's no free lunch. The demon has to gather information. It has to see the atoms to know if they are fast or slow. The act of gathering that information, of measuring the atoms and storing that knowledge in its memory, must create at least as much entropy as the sorting process reduces. The demon has to pay an entropy price for its knowledge. Information, it turns out, is physical. It's not just an abstract idea, it takes energy to create it, to store it, and to erase it. This is a huge step. We've gone from information as a message in a wire to information as a fundamental part of physics, tied to energy and disorder. Information isn't just something we use to describe the world, it seems to be woven into the fabric of the world itself. This leads us to the second, much bigger question. Is the universe made of it? This idea is most famously associated with the physicist John Archibald Wheeler. He was a giant in the field, a colleague of Einstein and Bohr, and in his later years he became obsessed with this question. He came up with a phrase to capture his idea, a kind of mantra. It from bit. What does that mean? It refers to everything, every particle, every force, every star, every galaxy, all of physical reality. Bit refers to the fundamental unit of information, the yes or no answer. Wheeler's proposal was radical. He suggested that at the bottom, the universe is not made of matter or energy. It's made of information. The physical world, he argued, emerges from the answers to yes-no questions posed at the quantum level. To understand this, we have to touch on the weirdness of quantum mechanics. In our everyday world, things are definite. A ball is either here or there. A cat is either alive or dead. But in the quantum world, that's not true. Before it's measured, a particle like an electron doesn't have a definite position. It exists in a superposition of all possible positions at once. It's a wave of probability. The same is true for other properties, like its spin. It can be spin up and spin down at the same time. And it's only when you make a measurement, when you look, that the particle is forced to choose. The wave of possibilities collapses into a single, definite reality. The electron appears at a specific spot. Its spin becomes either up or down. Wheeler saw this process as fundamental. The universe, at its most basic level, is a constant series of these quantum events. Each event, each measurement, poses a yes-no question. Is the particle here? Yes. Is the spin up? No. Each of these questions, when answered by nature, generates a bit of information. And out of this storm of bits, Wheeler proposed all of physical reality that it takes shape. The observer is central to this idea. The act of observation isn't just a passive looking. It's an act of creation. It's what turns quantum uncertainty into physical certainty. This doesn't necessarily mean a conscious human observer. Any interaction that forces a quantum system to settle into a definite state counts as a measurement. A particle hitting a detector, a photon of light bouncing off an atom. So, in this view, the universe is participatory. We don't just live in it, we are part of the process that brings it into being. By asking questions of it, by measuring it, we are helping to define it. The reality we see is the sum total of all the answers to all the yes, no questions ever asked. This is a mind-bending idea. Is it just a strange philosophical speculation, or is there any scientific reason to take it seriously? Surprisingly, there is, and some of the best evidence comes from the most extreme objects in the universe, black holes. A black hole is an object so dense that nothing, not even light, can escape its gravity. When something falls into a black hole, its information seems to be lost forever. If you throw a book into a black hole, all its intricate information, the words, the story, the chemical makeup of the paper and ink is seemingly crushed out of existence. This created a huge problem for physicists. A core principle of physics is that information can never be truly destroyed. It can be scrambled, but it must always be recoverable in principle. The idea that black holes were destroying information was a crisis. Then, in the 1970s, Jacob Bekenstein and Stephen Hawking made a stunning discovery. They found that a black hole has entropy, and its entropy is not proportional to its volume as you might expect. It's proportional to the surface area of its event horizon mode, the point of no return surrounding it. This was bizarre. It's like saying the information capacity of a room is written on its walls, not contained within the room itself. It suggested that all the information about everything that ever fell into the black hole is somehow encoded on its two-dimensional surface. The information isn't lost, it's smeared out and stored on the edge. This led to an even more radical idea known as the holographic principle. It was developed by Gerard de Hooft and Leonard Susskind. The principle suggests that what's true for black holes might be true for the entire universe. It says that all the information that makes up our three-dimensional reality might actually be encoded on a distant, two-dimensional surface that surrounds us. Think of the hologram on a credit card. It's a flat 2D surface, but when light hits it just right, it produces a three-dimensional image. The holographic principle suggests the universe is like that. We are the 3D projection. The fundamental reality, the code, is written on some vast cosmic boundary. If this is true, then the universe is fundamentally about information. The 3D world we experience is a kind of projection of that information. The its of our world are just a representation of the bits on that distant surface. This provides a concrete mathematical framework for Wheeler's it from bit idea. It's no longer just philosophy, it's a concept with deep roots in our best theories of gravity and quantum mechanics. There's another line of thinking that supports this, sometimes called digital physics. This idea suggests that if the universe is made of information, then it must be finite. You can't have infinite information, and if it's finite, then space and time themselves might not be smooth and continuous. They might be made of tiny, discrete units like pixels on a screen. There is a smallest possible length in physics called the Planck length. It's incredibly unimaginably small. The idea of digital physics is that the Planck length might be the fundamental pixel size of the universe. You can't have anything smaller. Each of these pixels of spacetime could represent a single bit, or a small number of bits. Our smooth, continuous-looking reality would just be an illusion, the result of these countless tiny bits interacting according to some fundamental program, some cosmic algorithm. In this view, the universe is literally a computation. The laws of physics are the software. The initial state of the universe after the Big Bang was the input, and the evolution of the universe, the unfolding of stars, galaxies, and life, is the output of this computation. We are not just living in a universe that processes information, we are living inside the information processing itself. So, we have these powerful converging ideas, from Shannon's definition of information, from the link between information and entropy, from Wheeler's it from bit, from black holes and the holographic principle, and from digital physics. They all point in a similar direction, that information may be more fundamental than matter and energy. But we have to be careful. We have to be honest. These ideas are on the cutting edge of physics, and they are not universally accepted. There are serious problems and counter-arguments. First, there's the problem of meaning. Shannon's information, which is the basis for all this, is specifically about quantity, not quality. A random string of bits has very high information content, but it means nothing. Our universe doesn't look like a random string of bits. It has structure, complexity, and laws. It contains meaningful information. A DNA molecule is not just a random sequence of base pairs, it's a code, a recipe for building a living organism. How does meaningless Shannon information give rise to meaningful information? This is a huge gap in the theory. It from bit doesn't explain how you get the specific it of a beautiful, complex universe from a random sea of bits. Second, there is the hard problem of consciousness. If you and I are just incredibly complex information processing systems, if we are just the output of a cosmic computation, then why does it feel like something to be us? Why do we have subjective experience? Why do we see the color red, feel the warmth of the sun, or experience the emotion of joy? You can describe these things in terms of information processing in the brain, but that doesn't explain the experience itself. A computer can process information about the color red, its wavelength, its frequency, but it doesn't see red. This is the mystery of consciousness, and a purely informational view of the universe doesn't seem to have an answer for it. If we are part of the it, our conscious experience is a fundamental part of that reality. A theory of everything must eventually account for it. Finally, there is a more philosophical objection. Are we just falling into a trap? In the 18th century, with the rise of clockwork mechanics, people thought the universe was a giant, intricate clock made by a divine clockmaker. In the 19th century, with the Industrial Revolution, the universe was seen as a giant steam engine full of heat and pressure and governed by the laws of thermodynamics. Now, in the 21st century, we live in the information age. We are surrounded by computers. So, of course, we see the universe as a giant computer. Is it from bit, just the latest metaphor, a projection of our current technology onto the cosmos? Maybe in 100 years we'll have a new technology and we'll have a new metaphor for the universe. Oh, it's a humbling thought. It reminds us that our understanding is always limited by the tools and concepts we have at hand. So where does that leave us? What is information, and is the universe made of it? We can say for sure what information is in a technical sense. It's the resolution of uncertainty. It's a measure of predictability. It can be quantified in bits. And we know that this concept is not just an abstraction. It is deeply physical, connected to the laws of thermodynamics and the very fabric of reality. As for whether the universe is made of it, we don't know. The idea is powerful. It seems to solve some deep puzzles in physics, especially concerning black holes and quantum gravity. It provides a potential framework for unifying the strange world of quantum mechanics with the large-scale world of Einstein's relativity. The holographic principle is a mathematically serious idea that physicists are actively working on. But it remains a hypothesis, a profound and beautiful one, but a hypothesis nonetheless. It leaves some of the biggest questions unanswered: the origin of meaning, the nature of consciousness, and the nagging possibility that it's all just a metaphor. Perhaps the best way to think about it is this. The quest to understand reality has always been about finding the most fundamental layer. We thought it was atoms, then we found it was protons, neutrons, and electrons. Then we found quarks and leptons. The it from bit hypothesis suggests that maybe the next layer down isn't another, smaller particle. Maybe the ultimate layer is not a thing at all. Maybe the ultimate layer is the logic itself. The rules. The bits. The answers to yes/no questions. Perhaps the tangible physical world we experience is an emergent property, a beautiful and complex pattern running on a much simpler informational substrate. We are still at the very beginning of this story. We are like people who have just discovered the alphabet and are now trying to read the epic poem of the cosmos. We've figured out what the letters are. They are bits of information, but we are still learning how they are put together to form the words, the sentences, and the meaning of the universe. The answer to whether the universe is made of information is not yet known, but the question itself has changed how we see everything. It has forced us to confront what we mean by real, and to consider that the world around us might be stranger and simpler than we ever imagined.